Okay, to finish this introduction on Lie groups and Lie algebras, I'm going to look at three important families of Lie groups that you encounter quite a lot. At least the first two, so the special orthogonal and the special unitary groups. So let's start with the special orthogonal groups. So special orthogonal groups. So these are SON. They correspond to the matrices, say lambda, so these are n by n matrices, such that lambda transpose lambda is the identity, and the determinant of lambda is equal to 1. So why do these often appear as symmetry groups? Well, that is because they preserve the Euclidean scalar product. So this is a symmetry group of the Euclidean scalar product. So meaning if I have two vectors psi and eta, and I just sum their components, so where psi and eta are n-dimensional vectors, then any matrix will preserve this inner product in the following sense. So because if we take one of these matrices and apply it to both vectors psi and eta, let's check that indeed we get the inner product of psi and eta back explicitly. So by definition, this is lambda of psi a, lambda of eta a. So let's write out in index notation what we have here. So this is lambda a b psi of b, lambda a c eta of c. And then we note that what we have here when we sum over the indices is really a matrix multiplication of the transpose of lambda with lambda. So explicitly this is psi b, lambda transpose lambda, index bc, eta of c. So if this equals the identity matrix, I get a delta bc here, so I'm just contracting b with c. Okay. Now one thing you should notice is that I have not used here the condition that the determinant of this matrix lambda is equal to 1. So in fact there is a larger group. So in fact SON is really a subset of the orthogonal group O of n. So this is the set of matrices lambda that are just orthogonal. And one should notice that if you have an orthogonal matrix and you're going to look at its determinant, so if I take the determinant of this equation on both sides, I get a 1 on this side, and here, well, the determinant of this product, but that's just the determinant of the product of the determinants. And the transpose does not change the determinant. So I get that the determinant of lambda squared is equal to 1. So this really implies the determinant of lambda is either plus 1 or minus 1. So the orthogonal group is only slightly larger than the special orthogonal group because, well, here of course you notice very well the special orthogonal group, they correspond to the rotations, while the orthogonal group also includes reflections. So it's slightly bigger in the sense that it includes at least one reflection, so a reflection has negative determinant, and then composed of all the rotations gives the full orthogonal group. So why do we focus on the special orthogonal group and not on the orthogonal group in general? And that is because this is not a connected group. So it is not connected. Why is that? Well, if I would draw the manifold structure of O of n, pictorially, I would have a manifold that looks like this. So it has two components. One of them is really SON, capital N. And the other one, what corresponds to the matrices that have determinant equal to -1. So here I have the identity matrix. So there is no way to reach a point in this disconnected part with a continuous path that starts at the origin. But we really would like to have connected Lie groups, because we know that the exponential map, for instance, is surjective on a connected group. So that's why we factor out this overall minus sign by looking at the special orthogonal group. So let's derive the Lie algebra of SON. So how do we do this? So what is the Lie algebra? So there are various ways to go about this. One way is just to say that, okay, we know that this is a connected group. It's also compact, so every element can be written as the exponential of a generator. So I know there will be some generators such that lambda is the exponential of e to the alpha a xa, where the generators xa and the number of them are still to be determined. And let me now just impose on lambda the restrictions, so the orthogonality and the determinant, and then just see what that means for the generators. And then I can just read off what this Lie algebra is. Okay, so for some xa generators. So let's see what that means. So if I know that lambda transpose lambda has to be the identity, but that is equivalent to saying that the transpose of lambda has to be the inverse. So what does that mean for this particular representation? So if I take the transpose of an exponential, that's just going to be the exponential of a transpose, which you can directly read off from the definition of the matrix exponential. And we also saw in a previous video that the inverse of an exponential is just the exponential of minus the matrix. So we want this to be equal to minus alpha a xa. And the only way for this to be satisfied for every choice of coefficients alpha a is by requiring that these matrices satisfy xa transpose is minus xa. So that means that xa are skew symmetric, or anti-symmetric if you like, skew symmetric n by n matrices. Okay? So that is one condition. Let's have a look at the other condition. So the determinant of lambda has to be equal to 1. And then we recall this famous formula that you may have seen before. If you take the determinant of the exponential of a matrix, that is the same as the exponential of the trace of a matrix. So this is equivalent to requiring that e to the alpha a x of a, okay, so the determinant of this is exponential alpha a trace of x of a. It has to be equal to 1, so it's equal to 1. So that says that these matrices should be traceless. Oh, but wait, we have skew-symmetric real matrices. All the elements on the diagonal will have to vanish. So their trace is automatically 0. So this is automatically satisfied for skew-symmetric matrices. Okay, so we've got all the conditions that we need on our generators XA. In particular, we now know that the Lie algebra, which by convention is denoted by small letters, and again I put a bar underneath to indicate that this is a Fraktur font. It is thus given by the set of matrices, or real n by n matrices, such that they are skew Hermitian. So X transpose is minus X. So this is my tangent space to the group SON. And from here it's easy to read off, for instance, what is the dimension of this Lie group. So we need to know the number of generators here, so the number of linearly inequivalent skew-symmetric n by n matrices that I can choose. So dimension of SON, so that is really the same as the dimension of its Lie algebra, so the number of generators. So we have to ask, okay, how many independent elements are there in a skew-symmetric matrix? So we know we have zeros on the diagonal. The upper diagonal terms can be anything you like, and then the lower diagonal ones have to be the negative of that. So counting the elements above the diagonal, you get exactly 1/2 n minus 1. Okay? So the next groups on the list are the special unitary groups. Special unitary groups. So again here we can look at the special version and the not so special version ON. So let me write them down, both of them. So U of n, so that's a set of matrices, say U. So these are complex matrices n by n, such that U dagger U is the identity, while SUN, it has the determinant restriction. So U C n times n, U dagger U is the identity, and determinant of U is equal to 1. Now here this is a bit more of a restriction than in the case of real matrices. Why? Because if I take the determinant of this expression, I get 1 on the right hand side, but here I get determinant, and here the complex conjugate of the determinant. So what I have on the left hand side is really the square of the absolute value of the determinant of U, which has to be equal to 1. So this is saying that the absolute value of the determinant of U is equal to 1. But in principle it can be any complex number of modulus 1. So in the special unitary case, we're really restricting this to be the positive real phase equal to 1. Okay. Now both of these, they also preserve a scalar product. Now it's not the Euclidean scalar product, but the standard complex scalar product, like the one you have in a Hilbert space in quantum mechanics. So it preserves complex scalar product, meaning, let's denote this a psi like quantum mechanics notation, where the only difference with the Euclidean scalar product is that I have a complex conjugate here. And really the way to check this is exactly like here. I show that if I multiply psi by a unitary matrix and eta as well, go through these steps where the only difference is that here I get an additional complex conjugate. So here I get, instead of a transpose, I get a conjugate transpose. U times U is equal to the identity. So I really get that it satisfies this. Okay. So in the orthogonal case, we said that we like the special orthogonal matrices better because they represent a connected Lie group, while the orthogonal ones do not. Here the distinction is a bit different because also the unitary group is connected. But the difference is that the unitary matrices, they include an overall phase, which we actually do not like that much. Let me write this down. So any matrix U in the unitary group can be written as U is some phase e to the I alpha times U prime for U prime in the special unitary group. Right, and it's not so hard to see what this phase has to be. I mean, taking the determinant on both sides, I see that the determinant of U is going to be, well, the nth power of this phase. So I have to take this phase to be the 1 over n power of the determinant of U to get a matrix U prime that has determinant equal to 1. So I can always do this decomposition for a unitary matrix, which essentially is saying that I'm taking a matrix from the special unitary group and multiplying by a diagonal matrix, or say a complex phase multiple of the identity matrix to get the most general unitary matrices. Now, these part that I write here, so the phase multiples of the identity matrix, they commute with all the other group elements. So if you like, the phase contribution here is like an abelian subspace within this Lie group. And that makes that this this unitary group is what is called not simple, where the exact notion of simple will only be introduced in a couple of lectures from now. But it's saying that it cannot be reduced to a smaller, it can be reduced to a smaller group. So it's not irreducible, if you like. It's not irreducible in a particular sense, while SUN is simple. And the simple Lie groups are again like the building blocks of more general Lie groups. So that's why we focus on the special unitary groups. Okay, now it's easy to write down the Lie algebra, again using the same strategy. So I write U is the exponential of alpha A xa. Then I have to require that U dagger is equal to U inverse. So this is saying that if I take the dagger of my generator and then take the exponential, it has to be equal to the minus this generator, which is really saying that these generators should be skew Hermitian. Skew Hermitian n by n complex matrices this time. Complex matrices. And then there is the requirement that the determinant is equal to 1. So the determinant of u, so that's now going to be the exponential alpha a trace of xa, like before, which should be equal to 1. So, just like here, it means that the generator should be traceless. Right? And now this is really an extra condition, because a skew Hermitian matrix is still allowed to have non-zero diagonal entries, because it can have imaginary entries on the diagonal. So this is an additional constraint. So that means that the, let me write the Lie algebra here, so SUN, so it's a set of n by n complex matrices that are skew Hermitian and traceless. And it is not so difficult to convince yourself that if you look at the dimension of this, that you are left with exactly n squared minus 1 independent components. Because on the top, above the diagonal, you can put complex numbers, so that gives you n times n minus 1, because they're both the real and complex and imaginary part. While on the diagonal, I can put on the imaginary numbers minus 1 because of the trace condition. So I get n times n minus 1 plus n minus 1. So that is n squared minus 1. Okay? So finally, just to flash to you the last family of groups, which are a lot less familiar than the special orthogonal and special unitary groups. These are the symplectic groups. So they appear in, say, problems where you have a symplectic structure or Poisson structure. So for instance, in Hamiltonian mechanics, but okay, admittedly, I've never encountered this symmetry or needed to understand this symmetry in a problem, but let me mention it anyway. So the let me be more precise. Compact symplectic groups. So what are these? Let me give the definition. SPN. So these are the complex matrices 2n by 2n that are unitary, and they satisfy the following constraint. If I take U transpose and then a matrix J, a fixed matrix J that I'll describe in a minute, that it preserves it under this conjugation, where J is the matrix 0, 1, minus 1, and 0. Okay. So the structure where you have, say, instead of a n by n matrix, but a 2n by 2n matrix is something you get in Hamiltonian mechanics, for instance, where the first n components are the positions of a particle, and the second n components are the momenta. So a phase space is naturally of dimension twice the configuration space of your system. And such a matrix J, it appears when you're trying to consider a Poisson bracket on this system. Let me just write down for you the corresponding Lie algebra. So it's very close to this. So you have now complex 2n by 2n matrices that have to be anti-Hermitian and satisfy the transpose is J minus JXJ. And from these two conditions you can derive that this group has dimensions, symplectic group is n times 2n plus 1. Okay, so why am I mentioning this additional family of groups? Well, the reason is that in the very last lecture of this course, we're going to look at the classification of all compact simple groups, or the irreducible groups. And the list that we've now presented on the board, it's almost all of them. So together, these families correspond to almost all compact simple Lie groups. Where again, this notion of simple, I mean the group being irreducible, is something that we will define later in a precise way. So what do I mean by almost? So I've given you an infinite list of groups. For each n, you get a different Lie group here. So there is an infinite number of compact simple Lie groups, but we've now found all but a finite number of them. So the only ones that are remaining are the so-called exceptional Lie groups. So these are groups like E8. They have all these interesting names. Okay, so as soon as you understand also the exceptional groups, then essentially you know all the possible symmetries, continuous symmetries that can arise in a compact fashion within a system. So next week we'll start looking at how these symmetries can actually be represented. So we're studying the irreducible representations, in particular those of SU2, which is really the simplest case. And then in later lectures we'll see how this can extend to the other groups in this list, especially the ones that are relevant for particle physics, like SU3. Okay, that's it for this week. See you next